And we're going to go by direct substitution. Okay, so for example, if you wanted to find the limit of, let's say, problem A, the limit of sine of x as x approaches pi over 2. And for problem B, the limit of secant 2x as x approaches 0. And let's say for problem C, limit sine of x as x approaches 5 over 6. Or 5 pi over 6. Okay. So for problem A, just like you would with if you had just any regular, limit that wouldn't turn the denominator into 0, you just plug it in. The limit sine of x as x approaches pi over 2 is just sine of pi over 2. And sine of pi over 2 is just 1. Okay. So if you wanted to kind of look at the graph of that, it would look like, bless you. Let's say this is your sine wave. That's your x, that's your y, and this is your pi over 2. Now, as you approach pi over 2, from the left, it's equal to 1. From the right, it's equal to 1. So as long as the limit is the same from both directions, it exists. So we have our limit. You don't have to draw the picture each time. That was just kind of a visual. Okay. So for problem B, we do the same thing. We just plug in our x. Secant of 2x as x approaches 0. We plug in our x, or our 0. It's just 2 times 0, which is 0. So it's secant of 0. Now, if you remember, secant of x is equal to 1 over cosine of x. So secant of 0, we'll just make that 1 over cosine of 0. Since cosine of 0 is equal to 1, you just get 1 over 1, which is 1. And for problem C, we have the limit sine of x as x approaches 5 pi over 6. Once again, you just plug it in. Sine of 5 pi over 6. And you get 1/2. Okay. I just kind of threw in C because I didn't want you to think it was always going to equal 1. Just threw in something else. Yes?
So with the, you do the inside first, of course, like for secant, you would do the inside first, so it's 2 multiplied by 0 equals 0, and then you would evaluate it with the function?
Yes.
Okay.
Any other questions on this one? All right. Oh, sure. All right. Okay. Now we're going to look at what they call special trig limits. These are two, you can call them special cases. They're proven using L'Hopital's rule, which we'll cover later on. But right now, it's kind of an introduction to them. Special trigonometric limits. sure I got down far enough there. Okay, now the first one is the limit sine of x over x as x approaches 0 equals 1. And the second one is the limit of 1 minus cosine of x divided by x as x approaches 0 equals 0. Kind of separate those there. Okay, so we'll do a quick example. Well, a couple of quick examples. Let's say if we wanted to find the limit. Okay, and we had the limit tangent x over x as x approaches 0. Okay, well, we couldn't just plug in the 0 because then we have a denominator of 0, wouldn't exist. But if we remember from trig that tangent of x equals sine of x over cosine of x. Now I'll kind of separate that. Then we can manipulate it just enough to use the special trig limits. Okay, so if we decide to make it the limit, and instead of tangent x over x, we'll make it tangent x over 1 times 1 over x. Just kind of separate it a little bit. Or you can just leave it as tangent x, actually, as it times 1 over x. Okay. Now if we do that, all we have to do is just replace tangent x with sine of x over cosine of x. Limit of sine of x over cosine of x times 1 over x. Okay. Now, multiplication is commutative, so you can switch the cosine of x and the x. Just kind of swap them. Same way you can have 2 times 3 and 3 times 2, you're just switching them up. So the limit as x approaches 0 is sine of x, switch those up, over x times 1 over cosine of x. Okay, now with the limit, all you have to do is apply the limit to both of the factors. So you have the limit as x approaches 0, sine of x over x times the limit as x approaches 0 of 1 over cosine of x. Okay. So we know from our special limit, our special trig limit, at the beginning that the limit of sine of x over x is equal to 1 as x approaches 0. So we know this is just going to equal 1. And if we actually plug in the 0, we get 1 over cosine of 0, which is also 1. So we end up with 1 times 1, which is just 1. Okay. Any questions on that one? All right.
Sorry, real quick.
Mhm.
So you just, the sine of x
Mm-hmm.
and the cosine of x, you flip the denominators just because it's multiplication. It
Yeah.
doesn't matter.
Yep.
So,
Yep. As long as it's multiplying or addition, you can just switch them up.
so you made it simplified so we can solve it without using a calculator.
Yeah, exactly. Any other questions on this one? All right. Let's go to our next example. Oh, you still writing?
Go ahead, I'll get it later.
Oh, okay. Okay, so let's say, bring that down. We want to find the limit let's say you have sine of 4x over x as x approaches 0. To be honest, this is probably the most common use for it. You'll see this more than any other one. Okay, so if you have, I'll just rewrite limit of sine of x over x as x approaches 0 is equal to 1. Okay. Now the one thing we notice about this one is that the x here and the x here are the same. But would also be true if you had 4x here and a 4x there. So as long as these two are the same, then you can use this special limit. So all we have to do is get the limit of sine of 4x over x as x approaches 0 and multiply by 4 over 4. Because now we have 4 times x in the denominator. We can just get this 4 and move it out to the front. So as long as you just move it out to the front, you didn't change the value because all you did was multiply it by 1. So that's where you get the 4 over 4. Okay, so if we move this 4 here, we have the limit as x approaches 0. Again, we get the 4 in the numerator, just move it out front, so 4 times that. You have sine of 4x over 4x. Clean that up a little. Okay. So really, we just have 4 times this entire limit here. So as long as these two match, this limit will just equal 1. Which is just 4. Okay. Any questions on that one? All right. Leave that up for a few seconds. Yes.
This is leading up to something more, isn't it?
Oh, yeah.
Because I don't see no use for it right now.
Oh, yeah, this is kind of the, when everything's all nice and neat and works out, this is how it looks. Then we'll get a little bit messy as it goes on. So enjoy the nice and neat, because not all of them are nice and neat. Yes.
So the function, so what we're doing with the limits,
Mhm.
they're basically another like term for a function or whatnot. Like if that was just like f of x, is that like another thing, or is that, I'm going in a totally wrong direction? Because I know like we're supposed to find a limit for it, but then we're using the constant to multiply the 4 with.
Well, the limit is really just the value of a function as it approaches a certain point. So that's all it is. So as this value gets closer and closer to 0, we're just finding, okay, well, what's the value as it gets closer to 0? Even though we can't find out what it is exactly at 0, just because it'll make the denominator, it'll make it undefined.
Right, so we're trying to find a limit that makes it as
Yep,
close
as close as possible, yeah.
Okay.
Okay. All right, any other questions on this one? All right, so I'll do one more example like this. Let's say if you wanted to solve the limit as x approaches 0 of sine of 8x over x. Okay, that's the exact same problem. The only difference is you'd multiply it by 8 over 8. So you have the limit as x approaches 0, sine of 8x over x times 8 over 8. So whatever is in here, if you just have to match the denominator to what's in here. So whatever is in here next to the x, you just multiply it, numerator and denominator, by that same value. So you have the limit as x approaches 0. Oh, forgot to bring it out front. Sine of 8x over 8x. So as long as these two match, that's just going to equal 1. So you really just have 8 times 1, which is just 8. All right, so everybody's okay with that one? All right. Okay, so let's use our other limit. So if we want to determine the limit, let's say we have as x approaches 0, sine of x times 1 minus cosine of x divided by 2x squared. Oops, clean that up. There we go. Okay, so with this one, we can't plug it in because if we plug in 0, denominator 0, it's undefined. But if we manipulate this just a little bit, okay, so the first thing I'm going to do here is get rid of that 2. Just bring that out to the front and make it 1/2. So just bring your constants out to the front. Okay, so we have our 1/2 times the limit as x approaches 0. Sine of x times 1 minus cosine of x, all over x squared. So all we did was just get rid of the 2 down there. Okay, now this x squared, let's make x squared equals x times x. Okay, so now we just have our 1/2 times the limit as x approaches 0, sine of x over x. Well, actually, just keep these together for now. 1 minus cosine of x over x times x. Oh, forgot 1. Okay, so since it's all multiplication, we're just going to get these 2 and just separate them. Bless you. Okay, move that up a little bit. So you have 1/2 times the limit as x approaches 0, sine of x over x times 1 minus cosine of x over x. Okay, so now we just get that limit and we sort of distribute it to each of the factors. So 1/2 times the limit sine of x over x as x approaches 0. We're going to have that times the limit 1 minus cosine of x over x as x approaches 0. Okay, so we know just from the special trig limits that will end up giving us, we still have our 1/2 out here. The limit of sine of x over x as x approaches 0, we know that's 1. But the limit of 1 minus cosine of x over x is 0. So after all of that, we end up with 0. Okay. Any questions on that one?
reason why it was,
Mhm.
0 is because of, 1 minus cosine of x
Mhm.
over x is 0.
Yep. If it would have been any other limit on that side that had a different value, then you would just multiply all three together. But because it was that one and it equaled 0, that one just pretty much made everything else 0. Yes?
This is only when x approaches 0, it can't be any other value?
Nope, just as x approaches 0.
Gotcha.
Yep. Any other questions?
So you're breaking it down to those 3 basically principles that you gave us in the beginning
Yeah.
for each one.
Mm-hmm. All right. This was number, make sure I keep these in order. Okay, so now we're going to go over what they call the squeeze theorem. Some books out there actually call it the sandwich theorem, but same thing. And it states that if you have let's say you have 3 functions. So you have a function h of x, and that's less than some function f of x, and that's less than some function g of x. For every value of x, in an interval where you have some value of c. Except possibly at c itself. Got to put a period there. Also, let's say the limit of that first function h of x as x approaches 0 equals some number, we'll just call it L. I have no clue what the limit is, it's just some number. Let's say also the limit of the function on the outside g of x. Oh, sorry, that should have been x approaches c. I still have 0 on the brain from the previous one. As x approaches c equals the same limit. Then the limit of f of x as x approaches that same c exists and is equal to L. Okay, so if the limit above it has a, well, if the limit above it has a limit of L and the limit below it has a limit of L, if we draw that out, say, let's say this is some g of x, and this is some function h of x. Okay, so we know for every x value, f of x is either, well, it's going to be both above h of x and below g of x. So it can be anything it wants here, but at some point, as it's approaching some c value, it's going to have that same limit of L that the other two have. Because if it's always below h of x and always above g of x, or is that the other way around? Yep, always below g of x and always above h of x, then wherever h of x is a point and g of x is approaching, as it's getting closer and closer to that c, it's kind of forcing the f of x to go there too. Okay, and this is useful when you're trying to find the limit of really funny looking trig identities. Okay, so let's start off with a quick couple of examples. Oh, I'll give you a minute to finish writing that down. Oh, forgot to mention that this is the f of x here.
So L could be anything in between.
Nope, L is just this.
Just that one.
And this is your limit. So as this is approaching C, that's the limit.
Okay, so what's that squiggly line that you?
Oh, this is your f of x.
So it could be.
Yeah, f of x should be any function at all, as long as it's always below g of x and always above h of x. So it's kind of, which is why they call it sandwich, it's kind of sandwiched in between the two. Okay. Any questions on that one? Yes.
So it's basically saying if g of x has a limit and
Mhm.
h of x has a limit,
Mhm.
then f of x will have that same limit?
Yep, as long as it's between them.
And has that constant?
Yeah, exactly.
Or it's going towards that c?
Yes. All right. So it's kind of like saying if you have a 400-pound boulder on this side and a 400-pound boulder on this side, you're both walking towards a point. If they're walking towards that point, you're walking towards that point because no matter what, you're going where those two boulders go. So it's kind of like the same idea. All right. So let's say, for example, let's make sure I got that down far enough. Yeah, there you go. Say we want to use the squeeze theorem. To find, let's say for A, the limit of x cosine of x as x approaches 0. And for B, let's say, I'm trying to think of one. Let's say the limit x approaches 0 of I'll say x squared sine of 1 over x. Okay. Now, actually, with A, if you wanted to, you could have just plugged it right in, and you would end up with 0. Because you have 0 times cosine of 0, which is just 0 times 1, and it would give you your answer of 0. But it's mainly to just show you how the squeeze theorem works. Okay. So for A, all we have to do is remember kind of the basic ideas of cosine and sine. So if you remember, the values of cosine x are always between -1 and 1. So you remember sine, it's always just that value between -1 and 1. Okay. Which means we could write it this way. -1 less than or equal to cosine of x, which is less than or equal to 1. So it's always going to be between those two, no matter what value x is. Okay. So if we just get that and we multiply each one of those sections by x, then that will end up giving us -1 times x is -x, so less than or equal to x cosine of x,